Okay, we are going to solve problem 47 from the book, 47 chapter 2. And the problem is this one. Okay, we have someone at the top of a hill. He throws a stone upwards and it goes all the way up, reaches its maximum point and then comes down again. Okay, and there are some questions here. First question is, how much later does it reach the bottom? No? After we throw, how long it takes to go up and all the way down and get to the floor. And then the other question is, what is its speed just before hitting that point? And what is the total distance, not the displacement, but the total distance that it traveled? Alright, so let's write this down. Let's make our drawings. No? As usual, it's always helpful. And so here we are in the top of the hill. This hill is 70 meters high. Okay. We are throwing a ball up, so with a certain initial speed. The initial speed is 12 meters per second. If we think in terms of velocity, we need to associate with that a direction. I know it's up, but I don't know yet if up is positive or negative because I haven't chosen a reference frame yet. What else do we have? Well, it's not written explicitly in the problem, but we know G is pointing down. And now let's use the value of G, the correct value of G, which is 9.8 meters per second squared. Okay, all right. We have all the numbers there, but now let's choose a frame so that we can also give the sign. No, we can also associate the sign with the direction of this motion. So I'm going to be choosing, well, we're going to be playing with two reference frames. Okay, the first reference frame you can see here, we'll say that 0 is at the top of the cliff. Okay, and 0 is at the top of the cliff, and we are going to choose the reference frame pointing down. Okay, this is our first choice, and then we'll do with the other one. Okay, so my reference frame is this one. Okay, so positive is down, and I'm saying that the origin is here, so my initial position is right at the origin. My initial position is 0. Okay, once I made this choice, I can go and give signs to the velocity and to the acceleration. So the velocity is against my frame. It's against, so that means the velocity is negative. The acceleration is in the same direction as my frame, so the acceleration is positive. So this is very important. From now we can go on and solve these problems. What else can I say? Well, this final position here will be plus 70. Alright, so let's go. First question is, how much later will that stone reach that the floor? Well, if we want information about time, we have positions. Good way is to use that equation. Y is y naught plus b naught t plus g over 2t squared. What is the final position? Plus 70. What is the initial position? 0, so I'm not going to write it. What is the initial velocity? That one exists and it's negative. It's opposite to my frame, so minus 12t. What is G? 9.8. 9.8 divided by 2 is 4.9. Is positive because G is positive, t squared. Okay. So from here we can get the time. It's a quadratic equation. And so it's a quadratic equation, will give us two answers, and you can see the answers here. One is minus 2.7 and the other one is 5.2. Minus 2.7 does not make sense. Time is always positive, so the only answer that I have is really 5.2. Okay, then comes the other question with H. What is the speed? So if they're asking the speed, they don't really care about the direction, no? They just want a number. And they want to know what is the speed just before hitting the ground. If you want speed, let me go for the equation for the velocity. And I want to find this v, this is my unknown. My initial velocity I know is minus 12. G is positive, 9.8. And the time for the whole trip we already got is 5.2. So I just have to put 5.2 here and I'll get the velocity, which is 38.9 meters per second. What is the sign? This equation here will give us not just the magnitude but also the sign. And we know that the sign will be plus because my reference frame is plus. Now I'm going to be pointing down once I hit the ground, once the stone hits the ground, and so down goes together with my reference frame for this particular reference frame. But they don't care about the direction, they don't care about the sign, they just ask the speed. Okay, final question is, what is the total distance that we travel? For sure, we know that we travel 70, right? So once the ball came down, it goes up, reaches a maximum point, comes down, and from here to here it will have traveled 70. That we already know. Okay. What we don't know yet is how much does it travel up. Okay, so what do we need to know? How much it travels up. It will travel the same amount down, so we need to know this. We will add this and add 70. So basically we need to know this. We'll have this twice, 2 times, and then plus 70. So what we need to know now is how much it travels up. How can we do that? Well, to how much it travels up, it's information that we need about how far we go. We don't need information about time. So a good way to go is to use that equation. V squared is equal to V naught squared plus 2G delta Y. Okay. What is V squared, the maximum height? 0. What is V naught? And now the initial velocity is minus 12. Well, minus 12 squared is 144. What is G? G is 9.8. So we have 2 multiplied by 9.8 and delta Y. So this delta Y will be how much we travel up. So the value that we get here, we multiply it by 2 because we go up and then we go down, and then we add 70. And all that will give us 84.7 meters. Alright, now let's solve exactly the same problem but changing reference frame. Okay, so it's exactly the same problem. Here we are in our hill. The hill is again just 70 meters. Okay. And my G is of course pointing down. Magnitude is 9.8 meters per second squared. V is pointing up. V naught is pointing up and it's 12 meters per second. Okay. Now we are changing the reference frame. Instead of pointing down as we did before, I'm going to choose the ground floor as my origin, and I'm going to choose my frame pointing up. Okay. Of course I have to obtain the same answers. Okay, this reference frame is arbitrary, it just serves as a guide, but the answers will not change because of this choice. Okay, all right. If I chose my reference frame going up, and if I chose this point here, this position here as being 0, as being the origin, then my initial position now, my initial position is plus 70. Okay, plus 70 meters. Okay, with this choice of reference frame, my initial velocity is pointing up, so together with my frame, this is going to be plus. So different from what we had before. and my G, which is pointing down, is opposite to the frame, so it will be minus. Okay, that's it. All of the rest will be the same. So let's solve just the first problem, the first question, which is how much later does the stone reach the bottom? How much later? I'm going to go for the same equation that we discussed before for position. Right, so I'm just rewriting it here. And how are we going to write the values now? Well, now my final position is 0. Okay, my initial position is 70 plus 70. Yeah? What is my initial velocity? Plus 12t. And what is g? Now g is minus 9.8 divided by 2 is 4.9 t squared. So again, I have a quadratic equation. If I solve it, again, I'll get these two results and I'll get rid of the negative value. So the idea is exactly the same. It's just the signs that change because I changed the what I was calling plus in my reference frame. And also I changed the origin. So I changed the value of my initial position, but the results are all the same. Nothing changes because of the reference frame. Okay? The physical results are all the same. Okay, let's talk a little bit about graphs now. Graphical representation of those motions. All right. When we have uniform velocity, it's a simple motion, and what I can plot is the position versus time. So suppose I have position in meters, time in seconds, and I'll have straight lines because my velocity is just constant. I don't have acceleration, so I'll have just straight lines for the velocity. What is the information that I get from this kind of plot? The slope of these straight lines give us the velocity. Why? The slope give us the velocity because the definition of velocity is the average velocity, delta t divided by displacement divided by time, delta x divided by delta t. So the slope is delta x divided by delta t. This gives us the slope of that curve. Okay. So how can we compare all of these curves? Well, here the red one, the position is not changing, so we are not moving at all. It's not just the acceleration that is 0, but the velocity is also 0. And if I compare the black with the blue, of course, the bigger my slope is, the larger my velocity is. Okay? And if I look at these two motions, I go, my final position, my position at later times is larger than my initial position, so I know that this displacement is in the positive direction, so this velocity is in the positive direction. Okay, let's look at a different kind of plot now. So on the left here we had uniform velocity. On the left here our average acceleration was just 0, and our average velocity coincided with our instantaneous velocity. Now we are looking at a different kind of motion here on the right, and what we have on the right is uniform acceleration. Now the velocity does change. Okay, the velocity does change, and this is what we are showing this plot. We are showing the velocity versus time, velocity in meters per second times in second. And now the slope here tells us what the acceleration is. And so the slope tells us the rate of the change of the velocity. In this red curve, velocity is just fixed, it's not changing, so the acceleration, the average acceleration is just 0. The larger the slope, the larger the acceleration is. The average acceleration, which in this case average acceleration is equal to instantaneous, because we have uniform acceleration, the acceleration is not changing. Okay, so we got a lot of information just by looking at this graphical representation. So let me go on and start first with this kind of motion, okay, where the velocity is constant. Okay? So I'm showing to you an example of pieces. Okay, pieces. Each color here is a piece of motion in which the velocity is constant. So each piece here is a straight line. Okay, so we have here plot of position versus time, and each piece here has constant velocity because we just have straight lines. Okay, what can we say about each piece? Well, for sure, the acceleration is zero. For each piece, the acceleration is zero because the velocity is constant. The position is changing, but the position is changing at a constant rate. Okay? So, the acceleration for each piece is zero. What else can we say? The green piece tells us that the velocity is in the positive direction. How do I know that? Well, I know that because the displacement is positive. You see, my final position is 20, my initial position is 0, so my displacement is positive. Displacement is positive, then I know that my velocity is positive. What is happening to the blue one? Same thing. My displacement is positive because my final position is bigger than my initial position. My displacement is positive, so for sure I know that my velocity is positive. Okay? If I compare the green with the blue, in which piece do I have a bigger velocity? Well, in the blue, the slope here is bigger. No? So here I have a greater velocity. Alright, let's move on. The black piece. In the black piece, I go from 4 seconds all the way to 6 seconds with the same position. Same position means no motion, so no velocity here. So in the black, the object stopped, velocity is 0, no acceleration, no velocity, no nothing, we just stopped. What happened at the red? Again, we have constant velocity because we just have straight lines. But what do we see here? That now my final position is smaller than my initial. It's smaller, so that means my displacement is negative. My displacement is negative, so my velocity is negative. Okay? If I compare after this whole trip, after 8 seconds, what is the displacement and what is the total distance? Remember, displacement is just the final position minus the initial. Final position is 50, my initial position is 0, so my displacement is just 50. How about the total distance traveled? Well, here I went from 0 to 20, then to 60, so all the way here I traveled 60, and then from here to here I traveled 10 more. Now I went from 60 to 50, so I traveled 10 more meters, so my whole distance is 70. The displacement is 50, but that whole distance is 70. Okay, so this is a scenario where for each piece I had constant velocity. Now what we are going to do, well, this is just to give you the values of this slope. Now what we are going to do is to study plots for the case in which the acceleration is constant. Okay, if the acceleration is constant, the velocity does change. Okay, so let's start with this plot for the velocity, and let's study each piece, each color. Okay, so the green, it's all straight lines because the velocity the velocity changes at a constant rate. So each piece here has a constant acceleration. Okay, so the velocity is changing at a constant rate. Okay, so in the green case, let me put everything. In the green piece here, what we have is that the velocity is positive. I just look at the values of the velocity and I see plus 50, plus 100, plus 120. So my velocity is positive. Okay, so in this whole green part, I know that my velocity is positive. That's what this graph is telling me. And I know that the velocity is displacement always have the same sign, so I can even go ahead and say the displacement is positive. What is going on with the magnitude of this velocity? Well, the magnitude, look, it starts from 0, goes to plus 50, goes to plus 100, so the magnitude is increasing. So the magnitude of the velocity is increasing. If the magnitude is increasing and if the velocity is plus, then I know that the acceleration has to have the same direction of the velocity. That's what guarantees that the magnitude is increasing. So the velocity is plus, the acceleration is also plus. And I can know that from the plot, I can get even the value of this acceleration. The acceleration is this slope. So it's this delta v divided by delta t. Okay? Alright, it's constant acceleration because we have a straight line. What happens in the blue piece? In the blue piece, we still have velocity. No? It's a positive velocity. And if its velocity is positive, I can go ahead and say the displacement is positive. But the velocity is not changing. It's constant in this whole blue piece. No? So I know for sure the acceleration is zero. The acceleration is zero because the velocity is not changing. Alright, what happens in the black? Careful here. The black is telling us that the velocity is still positive. Okay, so it's very different from the previous plot that we saw for position. Okay, when in a plot for position I have a line going down like this, I know that the displacement is negative because it's minus position minus initial. Okay, so the displacement ends up being negative. When I go for a plot for velocity, things are different. Now, when I get this line going down, well, that does not mean what I see is that the velocity is still positive, okay? Because the velocity is just given by this. So, in this black area, my velocity is still positive, and velocity and displacement goes together. So here, my displacement is still positive. But what is going on? Well, what we can see is that the magnitude of this velocity is decreasing. Now the magnitude is decreasing. If the velocity is plus and the magnitude of the velocity is decreasing, then I know that my acceleration has to be opposite to the velocity. So if the velocity is plus, the acceleration has to be minus. And constant because we have a straight line. Okay? So the sign of the velocity is given by this number here. Okay, if we are above zero, the sign of the velocity is plus. Everywhere here the velocity is plus. In the case of a graph for position, then we have to look at the slope. If in a case like this, my final position is smaller than my initial position, so then the displacement is negative, right? Here, the velocity is plus because it's just above the origin. Okay, and then finally, in the yellow part. In the yellow part, the velocity is not changing at all. Velocity is not changing, I just stopped. No? I just stopped, I don't have acceleration, don't have velocity. And how about the red? Okay, red, I just go, I'm below zero. No? I'm below zero, so I know my velocity is negative. My velocity is negative, that means my displacement is negative. So now I'm moving in the negative direction. But I look at the magnitude of this velocity. The magnitude is increasing. I went from 0 to 50 to 100. So the magnitude is increasing. So if the magnitude is increasing and velocity is negative, I know the acceleration has to have the same sign. No? So minus for velocity, minus for the acceleration. I'm speeding up. My velocity, my magnitude of velocity is increasing and the acceleration is negative. Okay, now let's compare the same results with the results for a plot of position versus time. Remember, when we have acceleration, then the position versus time, position becomes a quadratic function of time. So we start playing now with parabolas. Okay. Whenever we have acceleration, we have parabolas. Now, acceleration is different from zero, we have parabolas. So whenever we have constant acceleration, the plots for velocity are linear in time, so straight lines. And whenever we have acceleration different from zero, the plots for position will be involving parabolas, okay? Because it's quadratic in time. Okay, so the green part, they are all analogous, okay? So the green part here, what we have is that we are moving in the positive direction because my final position is bigger than my initial. And as we saw here, my velocity, the magnitude of the velocity is increasing, so my velocity, my displacement is plus, that means my acceleration is also plus. Okay, plus acceleration, when we are talking about a parabola, we always say the following. If the parabola, if the quadratic term of the parabola is positive, we'll be dealing with parabolas like this. Okay, so this means acceleration is bigger than 0. This part also acceleration is bigger than 0. It's what people like to remind as a smile. A smile means positive acceleration. But when the parabola is a frown, so when it's pointing down like that, then the acceleration here is negative and the acceleration here is also negative. Okay, so in the green part, where the magnitude is increasing and the velocity is plus and the displacement is plus, so the acceleration was also plus. We have this mind. Here, where the velocity became constant, well, if the velocity became constant, there is no acceleration. Constant velocity means straight line. And that's what we have here in blue. Okay, here in black, the magnitude of the velocity starts decreasing. The velocity is still plus, so if it's decreasing, that means A is opposite, A was minus. A is minus here because, you see, we have the frown. Okay, so black is the frown. Now, velocity is still positive here, so displacement is still positive. And you can see also here, displacement is still positive. My final displacement minus the initial is still positive. Okay, the yellow one is when we stopped. We stopped, the velocity was just 0. Well, I stopped here, right? My position is not changed. Okay, we stopped and then the motion changed direction. The motion changed direction, my velocity became negative, that means my displacement is also negative. And we can see from here, my final displacement is smaller than my initial displacement. Okay, everything is negative, displacement is negative, velocity is negative, and the magnitude of this velocity increasing, so that means the acceleration has the same sign as the velocity, is also minus. And here we have the frown, so acceleration is also negative. Okay, so we got all the information by looking at these different pieces of those plots. What else can we say? Well, black, the black part, if I compare all of these different pieces, the black one gives us the largest magnitude of acceleration because this is the highest slope. And what is the maximum magnitude of the velocity? Well, I just have to go and see where do I get the biggest number. And the biggest number is here, is 120 meters per second. So that's it. That's the end of chapter 2.